lunar laser ranging. The principle is very similar to satellite laser ranging, but here, instead of the satellite, we use the moon. We use the moon. And they have put some arrays of reflectors like this over the surface of the moon through four Apollo missions, Apollo 11, Apollo 14, and Apollo 15. Apollo 11 has 100 reflectors, 14 has other 100 reflectors, and the third one, 15, had 300 reflectors on that. And they have put it on, created a triangle there. And this is the A11. And the distance between these points are 1,000 kilometers, 95 kilometers. They created a triangle, and from this triangle, they shoot the laser beam to these reflectors and received it back. Also, there was another mission which was not actually successful, L11 and L21. That which one of them, it was fighting by Russia, I think. We sent it to the moon, but they were not working. One of them, because of the dust that they take off the satellite spacecraft, I think it was this one. It's not accurate anymore, so it cannot reflect anything because of the dust due to the spacecraft that the spacecraft created there. So this is the principle is very much the same with satellite laser ranging, but the difference is that because of the longer distance from the moon, then the signal is very weak, extremely weak, comparing to the satellite laser ranging. They are satellite, they are 800 kilometers, 1,000 kilometers, something like that. But moon is much farther away. So it's very difficult to get detect the signal. But the good thing with moon is because of this long distance from the Earth, it has a very stable position and it's not very much perturbed. This is more stable than the satellite laser ranging. Satellite laser ranging are perturbed very well if they are closer to the Earth. But the moon movement is like that. So if you can successfully detect, if this is the Earth, detect the distance to the Earth with high quality, then its distance, if you have variations actually in the distance, they are not actually from the orbit and all that. So it's somehow more stable platform than satellite laser ranging, but it's too far and it's very difficult to detect. Difficult to detect the reflection. The reflection. For example, is the accuracy is very good, as I said. Okay, yeah. But the principle, mathematical principle. So if it is the Earth and it is the Moon and it's the center of the solar system, and we have a coordinate system for the Earth here, Z, this is gamma, this is X. Yeah, this is gamma, this one is X, and this one is Y. And we have a lunar coordinate system here. I do not draw the detail. I have a point at the surface of the sphere. I have the receiver. The coordinates of these 2 points can be computed simply from there. So if this one is O. So how do we do that? The ephemeris of the moon and ephemeris of the Earth is known. We can compute the orbit, this orbit simply these days. It's a simple integration or orbit integration. So the positions of the Sun and the Moon and the Earth with respect to the solar system is known. And the position of this Apollo, for example, reflectors, if you have this position known in that one, we have the position of this as known in the barycentric coordinate system, then the position of this point here with the barycentric coordinate system can be determined. So these two can be determined without problem. So what is the point for doing that? Because if let me draw with another color, then because this vector, rho vector, is nothing else than the difference between these two barycentric coordinates. So coordinates of the station, barycentric coordinate system, and the coordinates of the station, the reflector in the moon in the barycentric coordinate system. So in that way, I can have the vector, actually, this is a vector of this position vector. So we can determine the coordinate, we can write the equation for the vector pointing from the SLR station to this Apollo, for example, Apollo reflectors at the surface of the moon. So the absolute value of this range actually is nothing else than square of this distance. So if we have the coordinates of the station and coordinates of the satellite, so then we can somehow write this mathematical formula for the range. This is the range which is measured by lunar laser ranging, and the coordinates are there. Then we can measure the changes actually between the point at the moon and point at the sun, at the Earth, for geophysical purposes. This is because this movement of this moon in the space is more stable. It's much easier to measure this, for example, GM parameters of the Earth gravity model. It's good to determine length of day, universal time, and also for the tide and friction and many other geophysical phenomena we can measure by that.